Alright, I think I'm live. Hello. Hello. Yeah, I started, I think, a lot later than was scheduled, but especially on YouTube, if you're watching this on YouTube, I usually schedule it, but I guess I didn't really do a good job today. But yeah, I got like distracted again and again, which I'm very good at getting distracted. So yeah, unfortunately it's a very late stream. So yeah, I was kind of like tired coming home, so I decided to like take a long break, but the break was kind of just kept going, I guess. But I want to at least do a couple hours today. So I'll get something done, you know. Yeah. Hello, Alex. Welcome. Basically, the agenda for today is starting the ODE chapter 5, which I have open here. And this is like the stats document. I think this is a kind of like a cool document. You can barely see the text, but it's like so much that I've written. But it's to be fair, it's not maybe that much, but it looks cool, I would say. So yeah. I think I'll do at least 1 hour today. I don't want to do less, and I don't know. I feel like it's not really responsible if I do more. I'll just take the elf today, like the kind of like a late start and everything, and I'll be sure to do a longer stream tomorrow. But then again, I do wanna keep I still have the mindset of keeping a streak live, or keeping the a daily live stream streak, which I would say is a good thing. It's just on very rare days where it's maybe not convenient. But yeah. I think maybe we'll just start. Maybe. Let me just turn the clock on. There you go. It's late. 11:37 p.m. Only 23 minutes away from midnight. Alright, let me see if the audio seems fine. Alright. Cool. So let's start. On autonomous systems, chapter 5. Does this even work? Maybe it isn't working. There we go. How to know mass systems. Hello, Nilenka. I think you once mentioned you'll move. Will you stay in Sweden or go abroad? I'll move in the same town, basically. So I'll be here in Sweden. Yeah. And then I do want to do like a bachelor's abroad, or a master's, I mean. That's the plan, at least. Okay, so in autonomous, when doing this, okay, so the accepting. What does that mean? What is accepting? Well, this is just, I think this is a typo or something like. This should be like this should be accepting, right? I'm pretty sure. Like otherwise, it doesn't make sense. Okay, accepting the existing theorems since chapter 1 and certain examples in. We have up to now essentially concerned about linear differential equations. Oh no, it means okay. If we disregard chapter 1, I guess. Yeah. I've never seen that word used. Accepting. Is that just me? In contrast, the issue we will address in this chapter are primarily of interest in connection with nonlinear systems. We're going to restrict ourselves to the autonomous system like that, which I find fairly interesting. I mean, you can, in general, I guess, write an ODE like this, where f is from Rn plus 2 to Rn. Man, this one is lagging. Hello, Farast. Welcome. Yeah, so it's the zeroth. No, it's the zeroth derivative up to yeah, I mean, and x is defined to be x1 to x0, which is the same as x up until x. It's derivative. But here we just write it as xt, which is, I don't know. Let me just look at the 11 a.m. or p.m. It's the p.m. Yeah, it's p.m. So it's late night stream. Do I regret starting this late? Maybe a little. Or yeah, I guess most likely, but most certainly I do regret it a bit. But at the same time, I think I needed a bit of a break, to be fair. Anyways, so I have downloads. I just need to solidify my knowledge. Honestly, I feel like these streams are very useful to my knowledge. Today I had like a long discussion with friends, and I don't know. I noticed that we were talking about linear, like Fourier series and stuff, and definitely these streams. I felt that I could say something relevant. So xn we can write as this. It's called linear. Okay. Yeah. So Oh, I guess. Yeah. I think it was chapter 1. This is chapter 0. Or maybe not. Okay, yeah, well, this is the type I was talking about. And I think I'm kind of wrong here. It's just +1 since... I mean, in general, you would have... I mean, a general differential equation would be on the form... x prime up to x and n derivative. And then by using implicit function theorem, or to be able to locally solve it for any of these variables, I guess specifically for the highest variable, we can solve it for this. And then the and this is like a vector, or wait, maybe I'll not do that. Or yeah, I will do that actually. And yeah, so we have like a you can also depend on t, and I'm guessing, yeah, let me think. Doesn't matter, I think it does. I mean then we can have something like t times x or something like this. But in this case, we wouldn't have that. So we're not thinking about those systems. I mean, it's a good question why we're not thinking about those types of ODEs. I don't really know. Yeah, it's late here too. I'm studying late night. Yeah, I will start. It's 12 a.m. Oh, okay. Cool. ODE so cute. I don't know if I would call ODE cute. I'm not at that stage yet. What are you talking about for analysis? Instack is a demagogue? We're going to restrict ourselves to so-called autonomous systems, where if it's a function of open from an open region omega from Rn to Rn, which is not dependent on variable t. Exactly. So this is what I was thinking. We assume that f satisfies the Lipschitz condition in a neighborhood of every point in omega. Yeah, with this, existence and uniqueness of the solution of an initial value problem is guaranteed. And it's guaranteed in the entire set omega. I'm pretty sure. Let me think. Right, so if we consider, yeah, so we can just expand it. Let me, like, if we have a point, t naught, x naught, like this is the initial condition, we know that it's Lipschitz in a, like in an open neighborhood. Or wait, let me, yeah, so t naught, yeah. And we have that the existence theorem says that if we have that it's Lipschitz in this open neighborhood around this point, we have an interval around t0, which there is a unique solution. And then if we pick the boundary here, we can just extend it to until we reach the entire omega. I haven't really gone through it that rigorously, but I guess, yeah, that's the idea. Anyways, orbits, equilibrium points. It is in general impossible to find exact solutions of nonlinear systems. Instead, we aim at acquiring a qualitative image of the solutions by considering them as oriented curves on parameter form in Rn to every solution curve Tx of t in R cross Rn. There is an orbit t to x of t in Rn. Example 1. It is easily seen that the system... Okay, let's... Okay, so an oriented curve... gosh. Okay. Okay, I guess you could graph it like that. In x cross xn, there is an orbit. Okay, yeah. It's easily seen that the system has solution like that. Yes, I guess. The solution curves are spirals in x in R cross R2. The orbits are negatively oriented circles. In the x1, x2 plane. Oh, let me think. So negatively oriented. Does that mean let me think. Like if you have a velocity. Starting with you, alright. Cool, Samira. We see in the example that different solutions of any system may give rise to the same orbit. If x of t is a solution, then y of t plus x of t is a solution. Hold up. So we have those. Let me see. I see. t is equal to prime of t plus c, which is equal to f of x of t. I don't really understand this, like, I guess we consider x of t and y of s as the same curve in Rn if there is an increasing bijective function s of t from the interval ab to the interval a prime b prime such that x of t is equal to through every point x naught of omega passes exactly one orbit of the system. One. Both are solutions whose orbits pass through x naught. This implies that there are numbers t0, t1 such that x of t0 is equal to y of t1, which is equal to x naught. For z of t is a solution of the system. The uniqueness of the solution of the initial value problem implies that z of t, in particular, z of t and x of t have the same orbit. Okay, let's go through this slowly. This is a bit difficult to understand, not gonna lie. If there is an increasive bijective function from the interval ab to the interval a prime b prime such that okay, I guess, right, okay, this makes sense since basically we have curves, like two curves, and if they're the same, we can let me see. Okay, if I want to parameterize like a curve, I can have one xx I mean, I guess I can do this in many different ways. But in particular, when we do this set of equation solutions have the same orbits, Okay, I guess that makes sense. Oh, what was that? Oh, that was a book. Assume that x of t and y of t both are solutions whose orbit pass through x naught. This implies that there are numbers t naught, t1 such that right, so we assume a contradiction and or no. Or yeah. Oh, sorry. Yeah, so we're viewing x as like an vector, which is like different from what we did before. Just trying to wrap my head around that. Like usually we're just out for x, right? We don't really care about the vector, but here I guess we do. I mean, yeah, finding a solution x like with bold x is of course like it's equivalent to having found like x of t where it's not a vector. Sorry, I'm really getting the proof. Like in particular, so we assume that the opposite, that x of t and y of t are both solutions who pass through x naught. We're trying to show that through every point x naught in our set, that there is exactly one orbit that passes through this point. And then we show that right, so these can have two different t values that give the same initial point, or initial value x naught, and then we can construct another solution that has the same orbit as y, because of this argument. And I guess you can, this is true since s of t is like an increasing bijective function. So that means that they have the same parameter curve. Furthermore, z of t is a solution of the system. And it passes through x naught. So it has the same curve as right, so z of t and x of t has the same orbit, but x and y are not necessarily the same curve, but rather curves that just pass through x naught. Oh, sorry, I get it. We're defining z, so we're saying that z has the same curve as y, and by uniqueness z has the same curve as x, meaning that x and y are the same curve. So that's, and this is a contradiction since we're assuming that, or is it a contradiction? I mean, we're assuming that they're different curves. Send book link. I mean, there isn't really a book link here. You can't really find this book online. It's a horrible book. It's not a horrible book, but it's horrible in the sense that you can't really find it online. But which is kind of sad. But I've scanned it in, so at least the pages I'm actually working on is visible. Let me just think about this. Passes exactly one orbit. So what is it? So contradiction is for every point x naught passes, there passes not necessarily like one orbit of system x1. So let me think. Yeah, Yeah, obviously. Yeah, so they're not, we're assuming that they're not the same orbit. Or they're not the same curve, and then we show that they're the same curve. Yeah, sorry. I don't know what I was thinking though. Yeah, I mean, curves can be like this, have the same point, x1 or xy. I mean, if they're the same curve, it's trivial. The set of orbits of an autonomous system is called phase portrait. The orbits of an autonomous system is called its phase portrait. What the frick? Okay. In example 1, the phase portrait consists of circles around the origin. Example 11 in chapter 0 to 23, we have seen another example of the phase portrait of an autonomous system, Volterra-Lotka system. In both these cases, the phase portrait consists of closed curves. Let's see here. Yeah. So what is a closed curve? I also need to know, like, I don't know if I know the definition here. I mean, we have like a tangent vector. I mean, isn't like an oriented curve, like we have a set, like a defined like direction vector, and then we have the parameter, or like the curve itself. I guess. And if it's positively oriented, or I don't know how to spell. It's positively oriented. It's something to do with the, or rather, maybe it's like the normal. We're giving a normal here, normal direction. We have a curve, and we're given the normal here, and there needs to be like a special relationship. So maybe like it needs to be positively oriented, or let me like if we have a curve like this and it goes like around like this, then we have a tangent like this, and we have a normal. Okay. Because like if we pick the normal to be in here, oh, it's like it needs to go out maybe. Like in this case, if we wanted to have it positively oriented, we need to pick the normal upwards. Alright. Biscuits. think does it? I'm not entirely sure. Let's just ask ChatGPT. I think it's such that if we use the right hand rule, that we get something pointing outwards. If we pick the normal to be upwards, then yeah, okay, this would be the positive order, because then the third vector would be pointing outwards. That's how we define it, I think. How do we define a positively oriented curve? Also, what is a closed curve? I don't think I've ever heard of a closed curve. Okay, well, a closed curve is kind of obvious. Just a curve that starts at the same point it ends at. You know, I was thinking closed in terms of sets being closed. But I guess that's not how you should view it. The idea of positive comes from the convention of direction around a region in the plane. In the plane, positive oriented is one that traverses its enclosed region in the counterclockwise direction. Oh, okay, well that's but counterclockwise seen from where? Okay. If you stand with your thumb pointing in the positive Z direction, curl your fingers curl in the positive counterclockwise orientation. Yeah, I think this is the same here. In this case, I mean, I'm not really sure if that's I'm not really sure about that. In both cases, these phases consist of closed curves. By reasoning, as in the proof of theorem 1, one may show that the solutions are periodic. Okay, wait, before I move on, let me do some let me look. I have some problems, like some exercises that I need to do for tomorrow's seminar. Right, so it's repetition 2.7. Yeah, so it's 2.7. So okay, that's a lot of problems. Okay, holy crap, it's like 14. Okay, that's a lot. Yeah, I haven't done these. I don't know if I'll just switch subjects right now. Like, hopefully, I can do them tomorrow in the morning. A is real symmetric, then this is true. Show that. I think these are good exercises for me, honestly. Not gonna lie. Maybe I'll take a detour here, actually, because I think it's wise for me to spend some time on these guys. Not gonna lie. So what do we have, like 14 minutes left? Is it even worth it? Let's see here. You know what? Maybe it's not even worth it. Oh, bro. Oh, I forgot. I kind of messed up the stream again. No. Yeah, I started. Okay. Well, it is what it is. Stream is going alright on Twitch. Yeah, I mean, I guess I scheduled it on YouTube and forgot to change it on the restream. Yeah, I'm basically using restream to stream both on Twitch and YouTube, and I usually like scheduling it on YouTube, but yeah, it doesn't really matter. So I guess the plan would be for me to do like wake up early and then try to stream at least like 4 hours, hopefully completing all the problems. Alright, so we'll just continue here. Let me show that the solutions are periodic. Can I do this? Should I show this already? So given, so I guess this is a theorem. What do we want to do? But then the solutions are periodic. So if x solution of what was the name? Autonomous system. Of autonomous system x prime f of x of t, then we have that x is periodic. What does that mean? Let's see here. Then the solutions are periodic. And you would say that this is a phase portrait. Or just a solution curve. Solution orbit / curve. By using the terminology of the text of the book. And what more? That then the solutions are periodic. Okay, so what does periodic mean? Well, it means that if I input t, okay, so given period, or wait, let's think. Wait, is that bug? No, it's not. Alright, so given period t, if this is periodic, then t times some n is equal to x of t, right? I mean, for all n that are integers. But we know that right, so we know that so I want to show that they're the same, so what I'll do is I mean, they have the same orbit. I'm not sure if that's it. I mean, we show that. So here we show that. Is a solution for all constant c. So I guess we want to show that the solution is unique. I mean, do we assume, let's see here. We assume f satisfies the Lipschitz condition in every neighborhood of omega, in omega, right? So we assume this. Yeah, so by Lipschitz, or I guess by uniqueness. X of t plus tn is equal to x of t. I'm not sure if this is really, like, I think this is fine, but I actually am not really sure. I mean, to be fair, this, like, saying that, I mean, given curve x of t, and then if we have s of t bijective and increasing, then we have that x of t is equal to x of s of t. Is it really obvious? Or I mean, at least for me, I'm not really. Is this what it says though? Right, so I guess right. So they have the same curve, and we can like I guess we can like let's just do simple examples so my brain can handle this. So we have x, or rather, in this case we have the curve tt, and we call this x of t, and where t is between 1 and 0, 1 and 0, and then we can also have y of t, which we define as being 2t, but between 0 and t half. I guess the curves are the same, but y of t is not the same. So I guess what should the function s of t be? We know that s of t, I mean, if we define s of t to be equal to I guess t half, then we're pretty good. And is this increasing? It is obviously increasing. Is it bijective? It is bijective. If we define, I guess, the range to be appropriate, but to be fair, the range is all of R, so yeah, so it's bijective and stuff. So that makes sense. So we can always put. What if it's not increasing? I should rather say there exists s of t bijective increasing such that we have this. If there is an increasing bijective function s of t in the interval, solutions. Let's see more bits. Going to sleep? It's too late for me, or are you good night, Alex? I'm probably gonna end soon too. But yeah, I don't know if I want to get stuck on this. Like, how would a proof of this look like? So, I don't know. Like, given x of t, we have x1 of t, dot 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 xn of t, and y of t is equal to y1 of t, yn of t, and then we have that Okay, so t here is between a and b, and we have t between a prime and b prime. Obviously, like, if they have the same curve, since x and y same curve, for all t between a b, there exists a corresponding t prime such that we have that x of t is equal to y of t prime. I mean, I guess, can we not construct S to be like so t like what like can't wait, in this case this could be negative actually, and this would starting at 0, and then, or no, not maybe negative, but it would be 1 minus maybe. One minus. I guess it would still be increasing. Because here starting at 0, it would start at 1, and then it would go to 0. So we go from here to here, and this one will go from here to here. And in this case, like, wouldn't it be decreasing, like, for this one? I mean, obviously it wouldn't. No, I think it's actually kind of clear, you know, it's that it has to be increasing, to be fair, like Or I guess it doesn't have to be increasing. Or does it? Like... so... Right, and S would obviously be bijective, so there's no issues here, since we're mapping like every value from A to B. We can find a corresponding value T, or T prime, and then T prime is, let me think. I mean, why would it necessarily be unique, actually? I'm not entirely sure. Like, couldn't it be another like T star that would have the same, like, I don't think it necessarily needs to be unique. Yeah, this is not really like a good argument, I would say, or a good proof. It's not really a proof at all, you know, but let's just have something written down. I guess I'll ask ChatGPT for a hint, since I don't know if I want to spend this much time on this, but at least I've done something, which is good. Is it true that given two identical curves, x of t and y of t, that wait, no. Or rather t curves x of t y of t if Wait, maybe I misinterpreted everything. Is identical, then there is there I mean, I think it just alright, if they have the same orientation. Alright, maybe this was a fruitless tangent, but maybe not. Maybe this is just some obvious thing, honestly. Like, if we have two curves that are the same, we can always reparameterize it so that they're equal to each other. Yeah, I think that's maybe like something very, very trivial. Anywho, I think I'll end it here. I'm not sure if this was the best session, honestly, for me, but nonetheless, it was something. So I'm happy about it, nonetheless, and hopefully everyone else had a good time, and stuff like that. So yeah, I wish you guys a good rest of your night or day, depending on where you are. But yeah, I'm just gonna end it here, and I'll hopefully do a link or a stream tomorrow morning, which is at least a couple hours. So yeah, that's the plan. All right. I need to get going to bed. It's kind of late, so yeah. All right, I'll